What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere. In the Northern Hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia.
What would happen if we got to zero new emissions? Zero in every sector globally across the world, right? So zero in industry, heat, transportation, electricity, everything. Would the climate get better, worse, or stay the same? Going net zero does not leave us at the same temperature that we are at today. It leaves us at the same rate of adding heat that we are at today, about 3 watts per square meter radiative forcing. In mechanical terms, greenhouse gases act as a valve, not a sponge. I'm going to use an analogy here just to make this point crystal clear. If you're driving towards a cliff at 30 miles per hour, getting to zero new emissions is not stopping the car. Getting to zero new emissions is continuing at 30 miles per hour, okay? Doing nothing at all and continuing to add emissions would be going 30.4 miles an hour one year, then 30.8 miles an hour next year, then 31.2, okay, in this analogy. It is slightly worse, but as a society, when we are about to make decisions to the tunes of tens of trillions of dollars, we should probably acknowledge the fact that getting to zero or doing nothing at all gets us to exactly the same place at almost the same time. Virtually all discussion in the media, the papers from policy wonks, everything you hear from environmental groups, politicians, clean energy startups, it's all to solve the wrong problem. Getting to zero new emissions will have virtually no effect. So if this is the wrong problem, what is the right problem then? Well, to avoid further warming, and this is to say nothing of tackling the temperature rise that we've already experienced. To avoid further warming, we need to get the atmosphere back to a state of radiative balance, a little less than 300 parts per million CO2, which means we need to remove roughly 1 trillion tons of carbon from the atmosphere and counting. Now, if there's one thing that I can guarantee, removing that much CO2, removing 1 trillion tons of anything, and hell, given how dilute CO2 is in the atmosphere, quadrillion tons of stuff, that is going to take a lot of energy. And all of that energy, by definition, since every energy source has a carbon footprint, just how much energy is super critical here, okay? So here's our governing rule for any approach to solving climate change. Your entire capture system must permanently store more carbon than is emitted in its production and the production of the energy source that it utilizes. Now, when I left my life in Silicon Valley, it was to base a company, the organization Energy Impact Center, on this very premise, to discover the subset of solutions that could actually make a difference, that could actually go negative, that could actually solve climate change. You see, if you're not going negative, even if your favorite energy solution replaces a worse energy source, you're not making things better. You're still adding carbon to the air, which further increases the rate of heat addition. It's like punching a small hole into a sinking ship and then patting yourself on the back because you didn't punch a big hole. Low carbon energy does not fix the problem. Only extremely low carbon energy even has a chance. And before I get into which solutions can go negative, and I promise that's coming, we're going to discuss one more problem that the climate change discussion has fundamentally wrong as well. The real role that energy plays for most of the world. Although we don't perceive energy directly very much throughout the day, it's far more than just gasoline and leaving the lights on longer. Energy is embedded in food, in medicine, in buildings. Energy moves goods and people across the globe. Energy is in everything that you need, and energy is at the core of what you love about a prosperous world. Restricting energy, on the other hand, with higher costs, means real hardship is spread throughout every part of life. The poorer you are, the worse it hurts. This is why we decide to subsidize all types of energy, including dirty ones, as the benefits from inexpensive power have a truly profound positive impact on quality of life. For most of the world, especially the poorest, less access to energy could actually hurt them more than climate change would. And they would feel it immediately, every day, in everything that they do. Let's observe a very similar trade-off regarding energy that humanity has already made. We knowingly continue to pollute the air with particulate, causing millions of cancers and asthmas every year just to receive slightly cheaper energy. We have had the medical reasons and technology to replace coal for over half a century. But only one thing ever has: another cheaper form of power. Do we really expect a worldwide consensus on sacrifice now? Across all age, class, and creed? To combat a threat distant in time and place? What the climate elite ignore is that for anyone except the absolute wealthiest, electing for more expensive energy isn't even a consideration. One more constraint for our solution too, since I know it'll come up. Our solution must not induce rapid changes to precipitation patterns. To many of the poorest on this planet, this would accelerate the worst possible outcome. We have over 2 billion people who do not have the agricultural know-how, infrastructure, or capital in place to adapt their food production to any sudden changes, and they would be forced to abandon their homes with just a few years of slightly abnormal rainfall. So unfortunately, this pretty much rules out the quick and cheap geoengineering fix of reflecting sunlight. Even if it would have a long-term positive effect on crop growth, regional changes to expected water too little or too much can instantly send millions into starvation and relocation. Or worse, as we've seen in Syria and Central America, dire civil conflict. Okay, I promised a solution, right? Let's derive one from first principles. If your mathematical imperative is that we must account for previous emissions, and our societal bounding condition is that we must do so in a way that doesn't impose an economic burden, then we must take the very things that require energy and result in the release of carbon dioxide and force them by definition to capture and sequester carbon dioxide. In other words, we need to make fuels and products with hydrocarbons, just as we do today, but with hydrogen and carbon from the air instead of from the ground. In this scenario, nothing downstream, not behavior or infrastructure, needs to change. And energy consumption all of a sudden has the exact opposite effect on climate. If you use carbon from the air, the more people consume, the more prosperity we enable, the faster we will solve climate change. If you want to actually solve this problem and do so in a matter of years, not just decades, you just need to make carbon negative fuels and products cheaper than carbon positive fuels and products. This is a complete alignment of individual behavior, market forces, environmental health, and human well-being. But to do so requires extreme energy abundance and an extremely low carbon footprint. It's a high bar to meet. But when I started the Energy Impact Center just 2 years ago, we ran this calculation for every known technology and found only one source that even came close to meeting these requirements. I don't have to tell you guys this, but not only is uranium an order of magnitude more abundant, but it has 6 orders of magnitude the energy density of fossil fuels. 3 million times as much energy. And in order to solve climate change, all nuclear power has to do is produce heat just 3 times as cheap. In the last 2 years, my organization has interviewed over 1,500 experts across technology, industry, economics, policy, regulations, and more to figure out why this hasn't happened yet and what would it take to make this a reality. In that time, I've personally done over 100 site visits to research centers, power plants, universities, conferences in over a dozen countries, and I've asked over 10,000 questions along the way. This is all documented on the Titans of Nuclear podcast, and I welcome you to join us in this process of discovery if you're not already part of our audience. I will now give you a summary of what I've learned over the last 2 years, and we'll wrap up with a plan to get out of this mess. Okay, so what's stopping us from deploying this incredibly powerful technology? There is one problem, and only one problem with nuclear, and that is building and operating new nuclear plants costs too much. Now, before you raise your hand about public perception being a challenge, the facts simply don't support it. Orders dried up in 1978, before 3 Mile Island, because nuclear was too expensive. Orders dried up in 2008, before Fukushima, because nuclear was too expensive. Dozens of countries right now are desperate to build nuclear, but nuclear is too expensive. Public perception is a self-defeating excuse that nuclear engineers use for not building a cost-competitive product. We don't sell EPRs and AP1000s for the same reason we don't sell Segways. Over-engineering has priced it out of the market. If we come up with a cheaper energy product, no matter what the critics say, the world will rationalize buying it, just like they rationalize buying clean coal, natural gas, or toxic solar panels. The price of a modern nuclear plant is not driven by complexity inherent to the power source, but rather accumulation of bad decisions that drive up cost, scare the public, and yet stubbornly maintain industry-wide support. My team has spent the last 2 years compiling dozens, but let's start with 4 examples. 1, large construction sites. I almost couldn't believe it when last month I saw Vogtle bragging about having 8,000 construction workers on site. Yes, more jobs are great, but what you want is 8,000 people spread across 8 different reactors they're building with 1,000 people each. make a cheaper product, and you'll drive job growth by selling more of them. Vogel's construction design choices have guaranteed there will never be another gigawatt-scale nuclear plant built on American soil again. It's bad engineering. Number 2, forged pressure vessels. Does anyone know why the industry required forged pressure vessels? We didn't used to. Out of curiosity, I called up a few manufacturers to understand the difference between welding and forging. It was 1.5 versus 150 million. 100-fold. The roots of this requirement come from experiencing radiation-induced embrittlement of the weld filler material, which in the 1960s contained copper. Well, guess what? We have new weld filler materials now. And we have processes that don't require weld filler materials at all. A good engineer does not design the strongest possible equipment. They design the cheapest possible equipment that meets strength requirements. To stick with forgings is emblematic of how conservatism and tradition drives bad engineering. Number 3, airtight containment buildings. You guys know the difference between a hot pot and a pressure cooker? It wasn't a hot pot used at the Boston Marathon. Yet we require designing nuclear pressure cookers with hydrogen as the fuel and radionuclides as the shrapnel, increasing cost and decreasing safety. The design goal is to limit the flow of radionuclides in the case of an accident. That is antithetical to requiring the building itself to be a fixed volume in the presence of a heat source. No requirement for airtight containment buildings means no pressure buildup and no hydrogen buildup. And 99% of the source term moves just a couple feet. A few radioactive gases would escape, instantly dilute, and become a totally harmless part of our atmosphere, just like the sun creates totally harmless radioactive carbon-14 every day. Instead of accepting a little radioactive gas escape, we create a dispersal mechanism for an otherwise non-mobile source and demand an incredibly expensive structure to facilitate this. Light water or any reactors with inherently negative neutronics do not need a containment building. They just need a building. A strong roof is both safer and 100 times cheaper. We sit here criticizing the Fukushima operators for keeping generators in the basement when we sold them a plant that traps hydrogen. Let's take a little responsibility for our bad engineering. Mistake number 4, evacuation. As far as radioactive release goes, Fukushima was as bad as it could ever get for a light water reactor. The largest tsunami earthquake combo civilization has ever seen took out every single safety system, spilling 3 gigawatts worth of core melt on the floor. An expensive mess, but not a hazard if you just stay out of the room. But then our genius containment building turned the entire building into a pressure cooker and then shot out the radionuclides. And even then, the source term was in such low quantities that no one was ever in any risk. A competent emergency plan shouldn't even have evacuation on the table. But what's the nuclear way? We behave as if a meltdown is the greatest possible emergency that could ever occur. And through our actions, we in fact convince the rest of the world of that. So as a response to this attitude, the Japanese government goes in, and the first thing they do is unplug 1,000 elderly from vital medical equipment, evacuating them from the remainder of their lives. After that, they forcibly remove 100,000 people from their home for years, while they systematically destroy their land, all to clean up an insignificant amount of radioactive contamination. Chernobyl taught us exactly how much and what type of radiation causes harm. Fukushima proved that no light water reactor could ever come close in any circumstance. But instead of sticking up for ourselves and shouting from the hilltops that we should have less regulation than a campfire, we cower in fear and we invent ever more systems, further driving up cost. That's bad logic. That's bad leadership. That's bad engineering. Why is this? Why are some of the smartest people that I have ever met responsible for some of the worst design choices I've ever seen? I've got 2 words for you. Safety culture. As students, I'm not sure if you've been brainwashed yet, but as a working adult in nuclear land, arguing for safety wins every argument, even if the result is less safety. Selling safety is selling fear. It scares the public. It doesn't appease them. Safety is responsible for those domes that built up explosive hydrogen. Safety is responsible for evacuations, which, unlike light water reactors, do kill people. And even worse, safety is responsible for driving cost in every aspect of nuclear power, pricing it out of the market, enabling the proliferation of every other less safe energy source. If you hear your colleagues criticizing the Russians, consider this math. If we had a Chernobyl every month for the next 100 centuries, it would be safer than letting coal persist even just 1 more year. And we are responsible for coal by not providing society a cheaper option. When the industry says safety is our #1 priority, what they mean is selling safety is their #1 priority, not making the world a safer place. Increasing costs in nuclear is the equivalent of driving the public into far more hazardous alternatives. Our primary obligation to public safety should be to consider all downstream consequences of our decisions, including the hazards of non-consumption. This is the standard for designing rules in the transportation sector, in healthcare, in construction, in virtually every other industry that has some level of risk. It would be a different story if a meltdown was a uniquely hazardous threat, if it did result in millions of deaths. But we in this room all know better. The key to fulfilling our promise to the public is considering their interests with respect to all hazards they might face, not radiation. Let's summarize. In order to stop climate change, we need to remove 1,000 gigatons of CO2 in a way that doesn't require sacrifice. To do this, we need carbon-negative fuels and products that are cheaper than carbon-positive fuels and products. And to do this, we need to make nuclear 10 times cheaper than it is today. How? $1 million question, right? Okay. #1, hire competent construction managers. Even with all the nuclear-specific constraints, it has such an overwhelming advantage from a fuel perspective. Better project management alone would make it more cost competitive. Build the plants smaller and faster, borrow less money for shorter construction periods, and it'll be the cheapest power on planet Earth, like it once was. #2, regulate for overall public safety, not just radiation. Excessive radiation protection adds tremendous direct and operational costs to every aspect of a nuclear power plant. It comes to almost $10 billion over the lifetime of each plant. And despite this fact, every year we continue to increase control over radiation. Crazy. Even though it's regulated at levels 10,000 times lower than anyone has ever been hurt by it. Number 3. You're not gonna like this one. Engage the fossil industry to kick off a development spree. They know better than anyone how to construct large buildings with pipes in them. They have access to the capital, political relationships, and the customers. Once we build nuclear with direct air capture for them, all they need to start doing is pumping fuels from the air instead of from the ground. And nothing else about their business model needs to change. If the world builds the equivalent of 40,000 1960s gigawatt-scale light water reactors, we can capture 1,000 gigatons of CO2 and create roughly $500 trillion of carbon-negative fuels and products along the way. That might seem like a high number, but it's not. The energy industry is already $6 trillion a year, and so just over 20 years, it would be the equivalent of quadrupling its market size, which we should be eager to do to bring 3 billion people out of poverty. With this vision in hand, I now leave the future of our planet to the incredible talent within this room. I implore you, rise above the norms that shackle our industry. Shed the defensive posture that our colleagues adorn, and wear the title of nuclear engineer with the pride that it deserves. You here are the masters of the magic within the atom. You alone hold the keys to saving the world from climate change. Thank you.